Thank you very much. I'm not a professor yet, hope to be at some point in my career. Thank you very much for your nice introduction. So it's really a pity that we are not all in Vienna. I'm really sad about this. I really wanted to come to Vienna. I hope we will have the occasion to be all together another time soon. Can you see my slide? Okay.
Yes.
So today I want to talk about a paper that is a joint work with Lira, Mazzeo and Sáez, but it is about resolution of singularities for the network flow. And clearly I have to start by telling you what is the network flow. First of all, we consider a network a connected set in the plane. For today, I will restrict the analysis to the plane. It can be done more general. A lot of part of what I'm going to say can be done in RN or in more general manifolds, but let's stay into a Euclidean plane. And my network is composed of finitely many regular, embedded, and smooth curves. So smooth enough for my purpose. Let's say C2. And regular, with regular I mean that each curve admits a regular parameterization. That is, I have gamma that it is defined on 0, 1 to R2, and gamma dot is different from 0 for every x. What is the peculiarity of this problem is the fact that I have curves, but they meet at junction, and all the difficulty of the problems lies in this presence of a junction. What I want to do, I want to do a generalization of the so-called curve shortening flow, that is the one-dimensional analog of the mean curvature flow. So we have discussed a lot of mean curvature flow in this conference yet. So what it is expected to do, that the normal velocity of each curve is the curvature. My point of view is variational in the sense that the network flow can be understood as the gradient flow of the length. So this means that I want to decrease the length as much as possible with respect to the L2 inner product. So the length of the network is simply the sum of the length of each curve, and I want to decrease the global length of this network. So not the length of each curve singularly, but the global one. To do this, I have to allow the junction to move. So this is an important point, because if I simply fix the junction, then I'm simply try to find some segment between two points. Instead, I want to decrease the global length. Again, if we maintain the variational point of view, one sees that the normal velocity is the curvature, but since we have also these boundary points with junction, a condition appears at the junction. And the condition that appears at the junction is this one, that the sum of a unit tangent vector at the junction equal to 0. So there are several possibilities how to approach this problem. This problem is the one-dimensional version of the so-called multi-phase mean curvature flow. So in which instead of letting evolve only one set, we are letting evolve more than one set, like in this picture here. And one can focus, as I do, on the evolution of the boundaries, that is of the network itself, or one can focus on the evolution of the sets. One possible approach is with the Bracke flow. Currently, this approach was already contained in the seminal work by Bracke, but there are very interesting recent developments about the Bracke flow done by Kim and Tonegawa and Stewart. In this case, one prescribes a weak evolution law for the grain boundaries, so for the boundary, really for the net, but there is also a couple control motion of the grains itself. Other possible approaches are still with weak solution, with the so-called minimizing movement. I can put on these approaches the BV solution, for example. And a lot of very interesting work has been done very recently also with this approach. And these are the name of people that work on this. A lot of people that I'm going to mention are present at the conference. Isidoro Glondotto, Fischer, Hensel, Laux, and Simon. And then there is also an isotropic version of this problem that has been considered by these authors here. My point of view is different. My point of view is working with classical solution. And this point of view goes back to Brunser and Reintich, that they were interested in the problem because they wanted to see this problem as the singular limit of Allen-Kahn, multi-phase Allen-Kahn. And in this setting, I want also to mention Debner, Gatke, and Kozaka, that they study the two-dimensional version with the shape of a double bubble. And then exactly the problem that I studied, the network flow, has a lot of contributions, starting from Mantegazza and Vaga Tortorelli, then Magni, and then there is this very important paper by Ilman and Neves and Schulze. So the point of my talk is to describe this evolution with a system of PDE. So this means that I'm going to write an evolution equation for each curve. So I have, if I have n curve, I will have a system of n equation. And then there are some couple boundary conditions that are related to the junction. I think it's very worth to mention also the fact that there are a large group of people that it is interested in this problem because of the application, the physical application. So the problem has been introduced by Mullins, but it's what was interesting of the motion of the grain boundaries. So this is not my point of view, but I think there is an extremely interesting, also very recent literature about this. Okay, so now I come back to my point of view and I explain what is the main difficulty in the problem. So if we believe the variational nature of a problem and we look this as a gradient flow, I obtain the two conditions that I told you before, the one on the normal velocity of the curve and the one at the boundary. The condition that I got at the boundary is that anytime I have a junction, at this junction point, I see that the sum of the unit tangent vector has to be equal to 0. However, this condition here does not prescribe how many curves meet at one junction. Consider the case in which we have more than 3 curves that meet at one junction, like in this situation. One realizes easily that this situation is not convenient from the energetical point of view. This means that if I have a junction with where 4 curves or more than 4 curves meet, like in this example here, I can find another structure, another network with 1 curve more and 2 triple junctions that has strictly less length. So the energy of the yellow guy here is strictly less than the one with respect to the one of the 2 curves that intersect. So this means that I expect for almost every time to see only triple junction. And in the case of a triple junction, then the condition sum of the tangents equal to 0 reduced to the fact that we are asking that the angle at the junction sum up to 0, so they are equal angles of 120 degrees condition. I call regular network a network in which I have this angle condition for the importance in the problem, since I expect to see this network for almost all the time. So what is the kind of theorem that I want to prove with this evolution? So if I consider an initial network that can have also a junction not of order 3, but more curves can meet at the junction, then I would like to show that there exists the positive time and the set of discrete times T0 Tn that I called singularities, and an evolving network that satisfies this property. Between 2 singular times, so away from T0 Tn, my network evolves satisfying the curve shortening flow equation. So each curve satisfies normal velocity equal to the curvature. Then I want some continuity in the global interval of time. And then I also want that my evolving network at time 0 is exactly my initial datum. If the capital T, the maximal time of existence is infinity, I want to show that as T that converges to infinity, my network converges to a critical point of the length. And I want to show that there exists a limit, not up to subsequence. Moreover, what one wants to show is that between 2 singular time, the equation is well posed. This means that we have existence uniqueness. And so if there is no uniqueness, and this is the case, this non-uniqueness arises only after a singular time. So at some point I have singularity, and then I can restart the flow after the singularity in more than one way. If I restart the flow in more than one way, I want to classify which are these ways. And I also want a complete classification of singularities. Probably a complete classification of singularities is out of reach, at least for the moment. However, one can try to say something like, what is a generic singularity? Okay, so this is something that I would like to prove, that I have partially proven. In particular, I've proven the first 2 points. Point number 3, it's a work in progress under some condition. And this 4th point is the topic of today. Singularity classification, we have partial result, but the global classification, complete classification seems to be extremely hard. Okay, So let's come back to my problem with my system of PD. First of all, I want to show well-posedness between two singular time. So I suppose that my initial datum is a regular network, so only triple junction, only sum of angle equal to of a tangent equal to 0. And I want to show that for a short time, when there exists a good solution of a flow, and this solution has also to be unique. First of all, uniqueness has to be interpreted as in a geometric version, because the problem is geometric. I can always reparameterize the curve and find a new solution. So uniqueness has to be understood up to reparameterization. So the trick to do this is to pass from my flow, that it is normal velocity equal to the curvature, that it is degenerate, a second order degenerate equation, to something that is not degenerate. And to do so, I use the fact that the tangential velocity is not prescribed. In particular, the tangential velocity is not 0, but it's something that I can choose. Why it's not 0? Because if I have sum of the tangent equal to 0 at the junction, we are in the plane. Also, the sum of a unit normal is equal to 0 at the junction. I don't want that the junction split up. I want the junction to remain a junction. And if each curve move only in a normal direction, then cannot move at all, because I have a sum of a normal equal to 0. So this means that there is a tangential velocity, and since I have that the problem is posed up to reparameterization, I'm able to choose the tangential velocity that is more convenient for me. In particular, I pick up the tangential velocity such that the evolution equation become the yellow one, but it is the so-called spatial flow. So you have dt of gamma equal dx square of gamma divided by dx square. So this is the spatial flow. And for this flow, we have well-posedness. For the purpose of today's talk, one can read my theorem as follows. Given an initial network, let's say of class C2, here it's a little bit less, not so important, then there exists a positive time and a unique solution for this short time of class C1 in time and C2 in space. Let's state the theorem like this. So here it's more precisely stated with sober spaces, but so for the purpose of today is enough. And then clearly it's easy to show that there exists a maximal solution. The problem is that also if I work in this very special class, the class of network with only triple junction, this condition of a triple junction is not preserved during the flow. So it's not avoidable a onset of singularities. So a onset of network where more than 3 curves meet at a junction. So we have to deal in some way with an irregular network. So it's really true that for almost all the times I see only triple junction, but there are some times in which I see something different. And if I write an equation for each curve and the curve disappears, then I have a problem with my system. So the fact that singularities appear is not theoretical, but it's really possible that this happen, and we have a partial classification and some example. So this example that I'm showing here of singularity are all analytical example. One can precisely write them. So one situation is the case in which we have a grain, a region enclosed by less than 6 curve, when it's possible to compute the evolution of equation of the area, and the area decreases linearly in time. So at some point, this area is going to disappear. And also in general, but in particular in case with a lot of symmetry, it's clear that when the area disappears, also all the length disappear. So in this case, what we have a disappearance of a lot of curves, the curves that bound the region. And in this case, also the curvature blows up. And this is kind of expected if you think a case of curve shortening flows in which you have one single curve that disappears, and when disappears the curvature blows up. And this can be proven with Gauss-Bonnet theorem. I have also another situation in which the curvature does not blow up, but still I have a singularity in which a curve disappears. And the two examples are here. So this example here is the case of a network that has the shape of a theta. If these two areas are equal, then they decrease at the same rate, and it's possible to show that the unique possible singularity that appears is this one. This means that one of the 3 curves disappear, not everything disappears at a time. And in this case, anytime I have only one curve that disappears without any vanishing of area, then I'm able to prove that the curvature remains bounded. And this is a peculiar singularity related to my flow. In the case of curvature flow, does not exist this kind of singularity in which you have vanishing of pieces of your or revolving set, but not curvature bounded. And this is another case. Also in this case, you can show that this curve in between disappears. And you can construct the example in such that this curve disappears in finite time, as I show here. And it's the case in which the angle alpha is bigger than 120 degrees. Instead, you can also construct an example in which the curve disappears as t that goes to plus infinity. So these are the examples when I have to deal with this topological singularity in which the topological structure on my network change. And the problem here is that some equations are going to disappear when this happens. And we will see in a second when some curves are going to emerge after the singularity. To do so, I have to give a definition of a flow plus singularity, but remaining in a classical PDE framework. And so I go back to the beginning, to my dream theorem, and this definition that I give is this one. I suppose that there are some singular times, T1, Tn. It would be nice to show that they are discrete, but okay, let's suppose this for a while. And then I suppose that each curve of a network and the number of curves of a network is still to be determined, satisfied the network flow for between two singular times, and then I consider some continuity of my network during time. So to deal with this singularity, we have to find a theorem that allows us to restart the flow after singularity happens. So a short-time existence result in the case we have irregular initial datum. So when more than 3 curves meet. The very difficulty here is that some curves are going to emerge. As I show you in the beginning, I show you that the length of the object with 5 curves and 2 triple junctions was less than the length of the object with 2 crossing curves. So this curve number 5 has to appear at some point with its equation. What we are able to show it's this theorem here, that it is the result in collaboration with Lira, Mazzeo, and Sáez. So suppose that we have an initial network sufficiently regular with at least one irregular junction, that it's the case that it's of interest for us now. Then I can show that there exists a positive time and the solution, a network, an evolving network, so that is a solution of a network flow between for positive time and has only triple junction for positive time. And then converge to the initial datum as time goes to 0. And this convergence is the strong convergence possible. We have some continuity, converge uniformly. More than this is not possible because even if we have one junction with 3 curves but not correct angle, we will see an instantaneous jump of the angle. So we cannot have a C1 convergence. The interesting part of our theorem is that if we stay in my definition solution, but it is a bit strong because I'm working with classical solution, then we are also able to classify the possible flows out. So it's clear that there is not a unique solution, but I'm at least able to classify all possible solutions. And these possible solutions are related with expanding soliton. So for the last quarter of hour, I'm going to explain a little bit how this theorem goes. So the geometry that lies behind this theorem and why this expanding soliton appear. So first of all, let's consider a simplified version. So let's consider the case in which the initial datum is irregular, so more than 3 curves meet, but it's composed by half line. So something that is a straight segment, so something straight up lines. Okay, in this case, it's possible to show that there exists a solution, not with the PDE argument, but with a calculus variation argument. So first of all, what is an expanding soliton? An expanding soliton is a solution of my flow that does not change shape in time. It's only become bigger and bigger. It enlarges itself. It's self-similar by my magnification. So what does this mean? That I have my solution gamma, it depends on t and space x, that can be seen like lambda t, that is how much you increase in time. times n eta, that it is with a change of variable x divided by lambda. So this is what is said to be a self-similar solution. If I put this ansatz to be self-similar inside my equation, normal velocity equal to curvature, I obtain the equation of expanding soliton, but it's this equation here. And I also obtain the rate of enlargement, but it is square root of 2t. In the case in which I have my initial datum, that it is composed only by straight half line, then there exists at least one expanding soliton with this initial datum. So there is always exists solution to the problem. So even if I have this equation, but now it's reduced from a PDE to an ODE equation with the ansatz of being expanding soliton, one does not use the equation to show this result, but one uses this observation, the fact that expanding soliton can be seen like critical point of a length functional in the plane with a different metric, a negatively curved metric, this metric here. So one can envision this a little bit like the hyperbolic plane. So how one can show an existence? Okay, then my direction, my half lines, if I compactify R2 with G, with a ball, my half line defines some boundary point of the boundary of ball. And then what I have to do, I have to find a critical point of the length with this boundary datum. But this is tantamount to the Steiner problem. So I can find a minimizer of the length with this boundary datum. And this can be done in any metric space. So in particular, also in my case. So since the minimizer of the Steiner problem exists, whatever is the boundary datum, then I also have an existence of expanding soliton. Critical points are clearly more than the minimizer. Indeed, I said there exists at least one solution. One has also to notice that there are both stable and unstable critical points. So in particular, I want only stable critical point because I want a flow, but it is with only triple junction for all positive time. However, the proof can consider also unstable critical point. So how my general flow is related with this? So now I give the idea of the proof. To be more precise, I give you basically the asymptotic expansion of a solution. Okay, now consider the case in which you have any curve, not a straight line as initial datum. And for simplicity, we suppose that we have only 4 curves that meet at a junction. And as I said, I'm going to give you basically the expansion of the solution. So I suppose that there exists a solution. Clearly, I'm able to show that there exists a solution, but for the purpose of today, I want to show how this problem is related with the geometry of expanding soliton. So I suppose that there exists a solution. So I suppose that I can parameterize each curve. And so I see each curve as a map from RT times 0, 1. So with Qi, my space, the domain, to the range that is R2 times R plus, with Z space. So I see the evolution as something in space and time. And then, since I told you before that there exists object with 5 curves with length that it is less than one with 4 curves, I have also to suppose that I have this new edge, that is this new internal edge. And this new internal edge will be defined on this P. That is the space given here. So basically, X is considered between 0 and T. It's not defined on 0, 1, but it's something that evolves in time. Okay, if I have my solution like this, then I could do a blow up of the space, of the range of the domain of my problem and see how the geometry of expanding soliton appears. So why I want to do this kind of blow up? Because if I do a proper blow up, then what remains of this 4 curve is the direction of the 4 curves, for a unit tangent vector, and so reminds a little bit of my straight lines, if I choose the correct set of coordinates. So now I perform the blow up. So first of all, I do a blow up of the domain. So in this case, I have for each curve my Qi. And my Qi was 0, 1 times R plus. And the point in which I have problem is the junction. And the junction is parameterized by gamma I of 0. So I want to do a blow up of gamma 0. So I do a blow up around this point, but it is the point x equals 0 and t equals 0. and I do a suitable blow up, and my new space is this one here. So this means that I remove the origin, all the rest remain. So this is still the space that I had before, but instead of the origin, I put a semicircle, a half circle, a part of a half circle. And I do the same also to the space P that describe the curve that I have add to my problem. I do the same type of blow up. Basically, doing this blow up from the analytical point of view is simply changing the coordinates to describe the evolution. So I add this new set of coordinates, tau and s, that are defined in this way. Like tau is square root of 2t, and s defined by s divided by square root of 2t. These coordinates are valid around here on my semicircle, but not at the bottom. So to be precise, to deal with my problem, I will need 3 sets of coordinates, because at some point when t equals to 0, this explodes. However, for the purpose of this talk, I think it's enough to think about these 2 family of coordinates, t and x and tau and s. And I do the same exactly for p. So my new space, that it is the union of my qi and pH, desingularized, is the desingularized domain of a solution. So it's not enough to desingularize the domain, I need also to desingularize the range. I do very similar strategy here. So I have my space here, that is R2 times R positive. I have located the multiple junction in 0 for simplicity. And so the problem is where the multiple junction lie, that it is the origin at time 0. So again, I remove the point x1 equals 2 equals t equals 0, and I do a blow up. And I put this kind of paraboloid, that it is in the picture is finite, but it's something infinite. And indeed, I describe this paraboloid with this set of coordinates. Again, I will need another set of coordinates to say how, in a sense, this paraboloid attach here to the rest of R2. So again, my coordinates are valid only on the paraboloid, and basically usual x1, x2, and t coordinates are valid in R2 times RT plus. So this is the new space. And now I want to lift my equation, my problem, to this new space in which I have done a blow up both of the domain and the range. What does mean lifting my problem? Basically, since I have changed coordinate of the domain and of the range, it means I simply have to change the coordinate in the equation, but it is the equation of the spatial flow, which I'm working with, and see how my equation looks like in the new coordinate. And changing the coordinate, one arrive to an equation of this kind, in which I have eta. So this eta is again already reminiscent of a expanding solid, and then we will see why. So this is my equation written in my new set of coordinates, and together my equation, I have also my boundary condition. So I have the equation for each curve. So this should be an eta I, which curve satisfies this equation, also the new curve that I have added. And then I have still my boundary condition. Still I have the fact that a junction is a junction, but at a junction, if it's a junction with recurse, I have sum of a unit tangent vector equal to 0. Now my new problem is this system here together with this boundary condition. And to solve my problem, I need a boundary value problem that is also an initial boundary value problem with initial datum. So what is the initial datum? Since I suppose that my eta is smooth, I suppose that my solution exists and is regular enough, I can compute eta at time 0. And what happens? I see that the tau of eta at time 0 is 0. And so my equation reduced to this equation here. But this equation here is nothing but the equation expanding soliton written in the new coordinate. So basically, my initial datum in the new blow-up space is an expanding soliton. So this is what I show with this expansion. So putting all together now, I have my case, my situation with I have 4 curves. This is not a regular junction because it's not pre-curve sum of 120 degrees. But I have, what is important is that I have a memory of the unit tangent vector at this point. I do a blow-up of a space, both domain and range, and I can picture my blow-up something like this. So basically, this direction here are this point here on the boundary. And then I have my object here on the blow-up space. And I can construct a solution in the whole blown-up space. And what I see is that the reminiscent of all this junction here, it's only these lines. And then on the paraboloid, I satisfy this equation, since then I have an expanding soliton. How many curves I have is not important, because the number of curves that arrive here is only the number of half lines that appear from here. So it's only the number of points at the boundary of my paraboloid. For any type of, for any number of boundary point, I can find an expanding soliton with my direct method argument, basically, existing solution to Steiner. So, but there are more than one solution. I choose which is my preferred expanding soliton. I put my expanding soliton on my blow-up argument, on my blow-up space, and this is my initial datum. And then here I have again a regular network, only with triple junction, because my stable critical point only with triple junction, and I can let evolve it, because in all my my change of variable, my equation has always solution, because I have a whole Poisson-nest result for objects with only triple junction. So basically, like this, I show you if I have a solution, how does look the asymptotic expansion. With this method, one can construct an approximate solution and then use my approximate solution basically with a perturbation argument. I can construct the solution. So this is what the solution look like in the blow-up space. To obtain the solution in my original space, then it's only needed, one only needs to do a blow-down argument and see the solution. In particular, the solution will have only triple junction for all positive time, because when I evolve this object here, already at time 0 in the blow-up space has only triple junction. For all positive time, this object has only triple junction till you arrive to a singularity. And so when you blow down, you see only this triple junction. So what is important of the construction? The important of the construction is that in this new space, we have a very nice conversion to the initial datum. We have C-infinity convergence to the initial datum. Clearly, when you blow down, you cannot have more than C0. You cannot have C1 convergence. And what's the point is that one can show that to have a solution, one has to have this expanding soliton. So here I have constructed solution using the expanding soliton, but my expansion also show that it cannot be there a solution without the expanding soliton. So basically, the possible expanding soliton classify my solution that starts from my irregular network. And so like this, I can show existence of solution past singularity, because here I use this as initial datum. I can use what I see at the time t singularity for initial datum and can restart the flow. Okay, I think it's time to stop. Thank you for your attention.
Thank you for your very nice talk.
Thank you.
Are there any questions? Let me see who is asking a question. Okay. Apparently not yet, but let me ask you a question. Did you think about the anisotropic case? Here,
yes, but we have not done the entire procedure yet, and the difficulty is here. One can see already from the asymptotic expansion that there are some complications. So here, what we do, basically, we prove that we have a solution. So we suppose that we have a solution. We basically do the Taylor expansion of a solution. We find all the coefficients. And to do this, we have to put our ansatz in this equation here, and then we have to solve this equation that becomes an ODE for every coefficient. And in the case of in the isotropic setting, we can do this because we have some recursion, but it's a little bit of a miracle. So I'm not sure if in the anisotropic case I'm able to perform the same computation. But surely it's something that one can try.
Okay, thank you. I can see that Harald is asking, raises his hand. Harald.
Yeah, so, okay, maybe slightly related, but I mean, changing the energy slightly, you could weight the different curve with different energies, and you can also introduce mobility. So the approach should be possible to be used in such situation as well.
I think that the approach in principle can be used, but again, there is this difficulty to be sure that one can able to show the existence of approximate solution. Maybe it's possible, but I have not tried. With mobility, I think it's more reasonable because the ODE that you arrive will be very similar. So I hope one can show existence. But yes, the approach is possible. So it's possible to use the approach also with mobilities. I have not tried. So in principle, it could work.
Okay, thanks.
Thank you.